Welcome back. This is Module 2 of our course on Artificial Intelligence in Industrial Control Systems. And in this module, we shift focus entirely to the artificial intelligence side of the equation. In Module 1, we built a solid understanding of what industrial control systems are, their architectures, their protocols, and critically, the ways they differ from conventional information technology environments. Now, we're going to build the second half of that foundation. A clear, practical understanding of what artificial intelligence and machine learning actually are. And I want to be upfront about the goal here. We're not going to turn you into a data scientist. What we are going to do is give you the conceptual vocabulary and the mental models you need to evaluate artificial intelligence tools intelligently, ask the right questions of vendors and colleagues, and make informed decisions about where and how AI can be applied in your industrial environment. Let's get into it. Let me set the stage for what we're doing in this module and why it matters. The field of industrial automation is being transformed by artificial intelligence faster than almost any other sector. Analysts consistently report growth rates above 35% per year for industrial artificial intelligence adoption. That means the engineers, managers, and technicians working in these environments today will encounter artificial intelligence-based tools within years. Many already have. But there's a problem. A lot of the artificial intelligence content out there is either written for software engineers and data scientists, which means it's too technical for most industrial control system practitioners, or it's marketing material that overpromises and underexplains. Neither is helpful when you need to make real decisions about real systems. So here is our grounding principle for this module, captured in those three cards on the right. Artificial intelligence is a powerful set of mathematical pattern recognition tools. Artificial intelligence is not magic, and it is not infallible. And our focus is specifically on the artificial intelligence techniques that have demonstrated real value in industrial settings. Not everything that exists in the artificial intelligence world, but the subset that is most relevant to industrial control systems. By the end of this module, you will know exactly what questions to ask when a vendor tells you their product uses artificial intelligence and machine learning. Here are the 5 things we're going to accomplish together in this module. Let me walk through them briefly so you know what to expect. Objective 1. We're going to untangle the terminology. Artificial intelligence, machine learning, deep learning. These terms are used interchangeably in marketing materials, but they have distinct meanings that matter when you're evaluating technology. Objective 2. We're going to cover the 3 main families of machine learning: supervised, unsupervised, and reinforcement learning. Each has a fundamentally different relationship with data and a different type of problem it's best suited to solve. Objective 3. We'll look at specific model types and map them to industrial control system use cases, so you'll know, for example, which type of model is typically used for predictive maintenance versus process anomaly detection. Objective 4. We'll talk about data, because in my view, data quality is the single most important factor in whether an artificial intelligence project succeeds or fails. Most artificial intelligence failures in industrial settings come back to data problems, not algorithm problems. And Objective 5. We'll have an honest conversation about what artificial intelligence cannot do and where it fails. This is the part that often gets left out of vendor presentations, but is absolutely critical for anyone deploying artificial intelligence in safety-sensitive industrial environments. Let's start at the top. Let's start with the terminology, because the confusion between artificial intelligence, machine learning, and deep learning causes real problems in industrial conversations. Look at the diagram on the left. These 3 concepts sit inside each other like nested containers. Artificial intelligence is the outermost. It's the broadest term, referring to any computer system designed to perform tasks that normally require human intelligence. Importantly, artificial intelligence includes techniques that have nothing to do with learning, classical rule-based expert systems, for example, that simply encode human knowledge as if-then rules. These are artificial intelligence, but they are not machine learning. Machine learning is a subset of artificial intelligence. It's specifically the approach where systems learn from data rather than following hand-coded rules. This is the breakthrough that made modern AI so powerful. Instead of a programmer writing every rule, you give the system data and let it find the patterns itself. This is why the quality and quantity of your data matters so much. We'll come back to that. Deep learning is a subset of machine learning. It uses artificial neural networks with many layers to learn very complex patterns. This is what's behind things like image recognition and natural language processing. It's powerful, but it has real costs. It requires large amounts of labeled training data, significant computing power, and it produces black box models that are hard to interpret, which is a significant concern for safety-critical industrial control system applications. When a vendor says their product uses artificial intelligence, your first question should be, which part of this diagram? Is it a rule-based system, a traditional machine learning model, or a deep learning model? The answer has significant implications for data requirements, interpretability, and how you would validate it for your environment. I want to take a moment to address something that causes a lot of confusion, and frankly, a lot of hype in artificial intelligence discussions. The difference between narrow artificial intelligence and general artificial intelligence. Everything you have ever seen in a real product, every artificial intelligence tool, every ML model, every chatbot, every image recognition system is narrow artificial intelligence. Narrow artificial intelligence is designed to do one specific thing, and it does that thing very well. A model trained to detect bearing faults from vibration data is excellent at detecting bearing faults. Ask it to do something else, say, optimize a process set point, and it will fail completely. It has no ability to transfer knowledge the way a human expert would. General artificial intelligence, the kind you see in science fiction, the kind that can reason about anything, learn any task, and transfer knowledge freely, does not exist. It is a theoretical concept. There is active research in this direction, but no consensus on when or whether it will be achieved. Why does this matter for industrial control systems? 2 reasons. First, it sets realistic expectations. When you're evaluating an artificial intelligence tool for predictive maintenance, you're evaluating a narrow, task-specific system. It needs to be trained on your data from your equipment in your operating conditions. It won't generalize from someone else's facility. Second, and this is actually good news for industrial control systems, narrow artificial intelligence is more predictable and easier to validate than general artificial intelligence would be. A system that only does one thing within well-defined boundaries is much more amenable to the kind of rigorous testing that safety-critical environments require. Now, let's get concrete about what machine learning actually is mechanically. The diagram on the left captures the core insight. In traditional programming, a developer provides both data and explicit rules, and the system produces outputs. Think of a traditional alarm system. An engineer programs the rule. If temperature exceeds 450 degrees, trigger alarm. The rule is fixed, hand-coded, explicit. Machine learning flips this around completely. You provide data and the correct answers, the outputs you want, and the machine learning algorithm produces the rules itself. Instead of a programmer deciding temperature over 450 is dangerous, you show the system thousands of historical examples, normal operations and fault conditions, and it learns the complex multivariate relationship between inputs and outcomes on its own. It might discover that temperature at 380 degrees, combined with specific vibration and flow patterns, is more predictive of failure than temperature alone at 450. The machine learning lifecycle on the right is important to understand because it clarifies where most projects succeed or fail. Steps 1 and 2, data collection and feature engineering, typically consume 60 to 80% of project effort. Steps 3 and 4, the actual model training that people associate with doing artificial intelligence, are often the fastest part. And step 5, deployment and monitoring, is the one most often underinvested. I want to highlight this specifically for industrial control system practitioners. Industrial processes change over time. Equipment wears. Process conditions shift. Feedstock properties vary. A model trained on data from 6 months ago may not perform correctly on today's process. This degradation is called model drift, and without active monitoring, it's invisible until the model starts giving wrong answers, potentially dangerous wrong answers. Now, let's go one level deeper into machine learning and look at its three main families. Understanding which family a given artificial intelligence application belongs to tells you a great deal about how it works and what its requirements are. Supervised learning is the most mature and most widely deployed approach in industrial control systems today. The key requirement is labeled training data, historical records where you already know the correct answer. For predictive maintenance, this means historical sensor data with timestamps marked for fault events. The model learns to associate patterns in the sensor readings with upcoming failures. It is supervised because a human expert has to label the training data, telling the system this period was normal, this period was a developing fault, this period was a failure. Unsupervised learning is particularly valuable in industrial control systems because it doesn't require labeled data, which is often scarce in industrial settings. Instead, it finds patterns on its own. Anomaly detection is the classic unsupervised application. Train the model on data from normal operations, and it learns what normal looks like. Anything that deviates significantly from normal is flagged as an anomaly. You don't need to have examples of every possible fault. You just need good data from normal conditions. Reinforcement learning is the most exciting and the least mature for industrial control system applications. It learns through trial and error with a reward signal. DeepMind famously applied reinforcement learning to reduce cooling energy in Google data centers by 40%. There is active research in applying reinforcement learning to process control, but the safety challenges are significant. A reinforcement learning agent exploring suboptimal actions in a real chemical plant is not acceptable. For now, reinforcement learning in ICS is mostly limited to simulation environments and digital twins, which we'll cover in Module 8. Let's spend a moment demystifying neural networks because they're central to modern artificial intelligence and often presented as more mysterious than they need to be. What you're seeing on the left is a simplified diagram of a neural network. Each circle is a neuron, a simple mathematical unit that takes in multiple numbers, multiplies each by a learned weight, adds them together, and passes the result through a mathematical function. On its own, one neuron is trivial, but connect thousands or millions of them in layers, and the network can approximate extraordinarily complex functions. The training process, called backpropagation, works backwards from the network's errors. When the network makes a wrong prediction, the error signal flows back through the layers, and each weight is adjusted slightly to make the next prediction better. Do this millions of times, on millions of examples, and the network converges on a set of weights that captures the patterns in your data. Now, I want to be direct about two practical concerns for industrial control system practitioners. First, the resource requirements. State-of-the-art deep learning models can have billions of parameters and require powerful graphic processing unit servers to train and sometimes even to run. This creates a real infrastructure challenge in operational technology environments, which is why edge artificial intelligence, running simplified models on industrial hardware, is such an active area of development. Second, and more importantly, the black box problem. When a neural network makes a prediction, it's often extremely difficult to explain why it made that prediction. In a consumer application, this is an inconvenience. In a safety-critical industrial control system application, where you might need to explain to a regulator or a safety engineer why your artificial intelligence system triggered an alarm or recommended a process change, the lack of interpretability is a serious constraint. This doesn't mean neural networks have no place in industrial control systems. They absolutely do. But it means they must be deployed thoughtfully, with appropriate validation and oversight. Let's map the artificial intelligence landscape specifically to industrial control system applications. Not everything in artificial intelligence is relevant to industrial control. But these 6 technique families represent the areas where real, production-ready value is being delivered today, or will be in the near future. Time series analysis is foundational. Almost all industrial control system data is time series, sensor readings sampled every second, every 100 milliseconds, or even faster. Techniques in this family include classical methods like autoregressive integrated moving average and exponential smoothing, and modern approaches like long short-term memory neural networks that are particularly good at capturing long-range temporal dependencies. This is the backbone of predictive maintenance and process monitoring. Anomaly detection, I've already mentioned. It's one of the most widely deployed artificial intelligence capabilities in industrial control systems because it works with unlabeled data. The mature badge on these first two reflects that they have proven track records in production industrial deployments. Natural language processing is an area that's advancing rapidly due to large language models. The industrial application that excites me most is maintenance record mining, the ability to read years of unstructured work orders, technician notes, and failure reports and extract patterns that humans would never have the time to find manually. We're also seeing early deployments of natural language processing interfaces to SCADA systems. Computer vision is finding strong applications in visual inspection, using cameras with artificial intelligence to check for surface defects, structural damage, or gauge readings in places where continuous human monitoring isn't practical. Note the research badge on reinforcement learning. This is not a criticism of reinforcement learning. It's a powerful technique with real potential for process optimization. But deploying an agent that learns by trial and error on live industrial equipment is not something we can do safely today, without extensive simulation infrastructure and safety constraints. Of all the things I'll tell you in this module, what's on this slide may be the most practically important for your real-world artificial intelligence projects. Data is everything. The phrase garbage in, garbage out is old in computing, but it has never been more relevant than in machine learning. A mediocre algorithm with excellent data will almost always outperform an excellent algorithm with mediocre data. Yet in most artificial intelligence projects I'm aware of, the data infrastructure receives far less investment than the algorithm development. Let me walk through the three dimensions on this slide. Data quality is about whether your data accurately represents reality. In industrial control system environments, data quality problems are everywhere. Sensors that drift out of calibration, but keep reporting plausible-looking numbers. Communication interruptions that create gaps in time series records. Clocks that aren't synchronized across devices creating timestamp errors. And valves or instruments that stick and report the same value for hours. Each of these creates noise that can corrupt model training or cause models to learn the wrong patterns. Data quantity is about having enough examples. This is especially challenging for fault detection, because industrial equipment is designed not to fail. A compressor that fails once every 2 years gives you very few training examples of failure behavior. This is a fundamental challenge that the field is addressing through transfer learning, pre-training on data from similar equipment, and through synthetic data generation using physics-based models and digital twins. Data labels, specifically for supervised learning, require a domain expert to review historical data and mark which periods represent which conditions. This is expensive, time-consuming, and depends on institutional knowledge that may not be documented or may have left with retired employees. The quality of your labels sets an absolute ceiling on how good your model can get. The bottom strip shows your primary data sources in industrial control systems. The process historian is typically the most valuable. It's the long-term archive of everything your sensors have measured. If you're starting an artificial intelligence project, your first conversation should be with whoever manages the historian. This might be my favorite slide in the module, because what I'm about to tell you is exactly what a responsible artificial intelligence vendor probably won't lead with. But you absolutely need to know. Artificial intelligence systems fail. They fail in specific, sometimes predictable ways. And in industrial control system environments, understanding those failure modes before deployment is not optional. It is a prerequisite for safe operation. Model drift is perhaps the most insidious failure mode in industrial control systems because it's silent. A model that was accurate when deployed can slowly lose accuracy as the process it's modeling changes and give no signal that it's degrading. I've spoken with engineers who trusted a predictive maintenance model for months before realizing it had stopped working correctly because the operating conditions had shifted. Active monitoring of model performance. With automatic alerts when accuracy drops below a threshold, is not a nice to have, it's a requirement. Overfitting is the classic machine learning failure mode. It happens when a model is too complex for the amount of data it's trained on and learns the training data's specific quirks rather than the general pattern. The result looks great in testing, but fails on real data. The black box problem is uniquely challenging for industrial control systems. When an artificial intelligence recommends that an operator take a specific action, the operator needs to be able to validate that recommendation against their own understanding of the process. An unexplained recommendation from an opaque artificial intelligence model puts the operator in a difficult position. This is driving significant investment in explainable artificial intelligence techniques. Adversarial inputs and overconfidence are particularly relevant for industrial control systems cybersecurity. We'll cover adversarial AI in much more depth in Module 7. Let me distill this entire module into its single most important message. Artificial intelligence is not magic. I know that sounds obvious, but the way artificial intelligence is often discussed, in the news, in vendor presentations, in executive briefings, it can feel like something fundamentally different from other engineering tools. It isn't. Artificial intelligence is mathematics. Specifically, it's a family of mathematical techniques for identifying patterns in data and making predictions or decisions based on those patterns. That framing matters because it leads directly to the right questions. If artificial intelligence is a mathematical tool that works by learning patterns from data, then the quality of that data is the primary determinant of the artificial intelligence system's reliability. Not the algorithm, not the vendor, not the compute power, the data. And if the artificial intelligence learned patterns from data, then it can only be trusted within the range of conditions that data represented. Outside that range, it is extrapolating into the unknown, and unlike a human expert, it typically won't tell you it's doing so. These 3 reminder strips at the bottom encapsulate what I want you to take from this module. Data quality matters more than algorithm sophistication. All current industrial artificial intelligence is narrow, task-specific, and bounded. And failure modes must be understood and planned for before deployment in any environment where failures have physical consequences. Let's consolidate what we've covered. We began by untangling the artificial intelligence terminology landscape, establishing that artificial intelligence is the broad umbrella, machine learning is the subset that learns from data, and deep learning is the subset of machine learning that uses multi-layered neural networks. These distinctions matter when evaluating artificial intelligence products and making architectural decisions. We clarified that all current industrial artificial intelligence is narrow. Artificial intelligence, task-specific and bounded. General artificial intelligence does not exist and is not relevant to any current industrial control system procurement decision. We worked through the 3 machine learning paradigms. Supervised learning for labeled problems like fault classification and RUL prediction. Unsupervised learning for unlabeled problems like anomaly detection. And reinforcement learning, which is promising but not yet mature for live industrial control system deployment. We spent significant time on data because data quality is the single most important factor in artificial intelligence project success, and industrial control system environments have real, specific data quality challenges that must be addressed before model development begins. And we examined the failure modes that every industrial control systems practitioner must understand. Model drift, overfitting, the black box problem, adversarial inputs, and overconfidence. In Module 3, we bring both sides of our foundation together and look at the artificial intelligence industrial control system integration landscape, the architectures, the maturity levels across sectors, and the real barriers that determine whether artificial intelligence projects succeed or fail in industrial environments. Take a moment with those self-assessment questions before moving on. They're designed to help you connect these concepts to your specific operational context.